So we're going to start by looking at homogeneous equilibria. So what we're talking about is the same phase. So in our example here, we're going to have all gases. We could have all gases, so you will have to use the ideal gas law, PV equals nRT. Or we could arrange it because N over V would be molarity. So we could say that P equals concentration times RT. So what we're saying is that pressure is directly related to concentration, which is why we can use pressure in an equilibrium expression. So let's use the Haber process again. We've got nitrogen gas plus hydrogen gas in equilibrium with ammonia. So if you were going to use concentrations, you would want to call that Kc. So the brackets here would represent concentrations. And then the brackets here also concentrations. So this would be using molarities. So a Kc is using a molarity. If you're using partial pressures, then you have a Kp. So in this case, it would be the partial pressure of ammonia over the partial pressure of nitrogen times the partial pressure of hydrogen. Notice that we still use the coefficients. This 2 is here for the ammonia. It's also here for the ammonia. This 3 is here for the concentration of hydrogen. It's also here for the partial pressure of hydrogen gas. So let's say you were asked a question. You were asked to write for the Kp for this reaction. It's the synthesis of hydrogen fluoride. So you have to be able to write the balanced equation. We use our equilibrium arrows. We put the products on top, the reactants on the bottom, and then because these are gases, this would be a Kp. So this would be our Kp for this particular reaction. So let's look at another problem. We're given hydrogen gas plus iodine gas gives hydrogen iodide gas. We are given a Kp value of 45.9 at 763 Kelvin. The temperature is not a factor here. And we're given an equilibrium mixture contains a partial pressure of hydrogen iodide of 4 atmospheres, a partial pressure of hydrogen gas of 0.2 atmospheres, and we're asked to solve for the partial pressure of the iodine gas. Now you need to remember all of your diatomics. I like to use the device have no fear of ice cold beer. That gives me H2, N2, F2, O2, I2, Cl2, and Br2. So here is our reaction, hydrogen gas plus iodine gas in equilibrium with hydrogen iodide gas. First, you're going to set up your equilibrium expression. So that's going to look like this. It's going to be products of a reactants. And then we'll put in the values we have. And we have one equation and one unknown. So then when you do the math, you will get the partial pressure of the iodine. And you need to remember that because these are pressures, the units would be atmospheres. So this would be our answer. Okay, let's look at the relationship between Kp and Kc. So remember, Kp is the pressures, Kc is the concentrations. So here is the equation. The Kp equals Kc times RT to the power of delta N. R is the ideal gas constant, the 0.0821 liters atmosphere over mole Kelvin. So in this case, you do need to use your units. The delta N is the moles of the products minus the moles of the reactants. So let's look at a question here, which is giving us the K, which is, if you're given the K, this one is for the molarities, but we're asked first to write the K expression for Kp, and then we're also asked to find the Kp. So we have to know that phosphorus pentachloride is PCl5, and it's a gas. We have to use the equilibrium arrows. Dissociates means to break up. So the phosphorus pentachloride is the reactant. It says 2 phosphorus trichloride and chlorine gas. So those are your products. So here's the phosphorus trichloride gas. Here's the chlorine gas. So it looks like it's already balanced. We have 5 chlorines here and we have 5 chlorines here. So the question asks us to write the expressions. That means we need to answer what the Kp would do. And because this is gases, the Kp would be the partial pressure of the PCl3 times the partial pressure of the chlorine gas. So you took the products and put them on top. And because this is Kp, it's partial pressures. And then this was our reactant. So it went on the bottom. And then again, because this is gases, it'd be partial pressure. So if we look at our balanced equation, we have 1 plus 1, that's what gives us our 2. And we only have one of these, so that gives us our 1. So it's how many moles of products minus how many moles of reactants, whatever that is. In this case, 2 minus 1 is 1. So this delta N is going to go right here. So in this case, it is a positive value, but it does not always have to be a positive value. It could be a negative value. It's always going to be adding up the moles of the products and then subtracting the moles of the reactants. And if you have more than one reactant, you'll have to add those up as well. So we get our Kp, we were given the Kc, we put that in here. We use the 0.0821 liters atmosphere over mole Kelvin. And then in this case, you had to take the temperature and convert it to Kelvin. And then when we do the math, we get 1.24. So this is our Kp.